And my name is Xiaru. Currently, I'm postdoc here in the EPFL Microsystem Laboratory under the supervision of Jürgen Brugger. And today I will present you our recent work using nanofraser, that is thermo-mechanical nanocutting and nanostraining of 2D materials. First, I will introduce the opportunities and the challenges of 2D materials, then detail in the two techniques we developed, thermo-mechanical cutting and the straining at a nanoscale. So you may know 2D materials are referred as atomical thin materials or single layer materials. One of the most famous materials is graphene. The thickness about 0.3 nanometer, which makes it very flexible and stretchable. And more in the following materials like 2D semiconductors like molybdenum disulfide and tungsten disulfide exhibit promising potential in the flexible electronics. And some other transparent 2D electrodes actually contribute a lot in the solar cells and the batteries, and many other extraordinary properties in the mechanical and electronics components. Besides the single layer materials, actually, when you stacking the different types of material, 2D materials, which will bring you new materials and shows very different properties. Inspired by those opportunities, we are committed to solve some very important challenges regarding to the materials, device, and the systems. For the materials, actually means control the high quality material growth. And based on the device, actually we aim to fabricate like a high performance dedicated devices. And in this aspect, actually the wafer scale integration of the 2D circuits is one of the bottleneck challenge in this category. At the end, we aim to achieve like 2D systems consisting of maybe sensor, processor, memory, and transmitter. So actually in 2019, a common paper titled How 2D Semiconductors Can Extend Moore's Law is published in the Nature, and the paper briefly introduced the three challenges in this 2D committee. One is the discovery and of new 2D materials and predicting the properties accurately. Another one is the material growth and testing the samples. And the next one is sensing device performance. You may know the fabrication process, of course, will influence the significant the device performance. For example, the patterning method for the device fabrication and for the strain engineering for the high performance in the electronics properties and the optoelectronics properties. So next, I will detail the two parts we have done here. The first technique I will introduce is thermo-mechanical nanocutting of 2D materials. When we talk about patterning of 2D materials, what come to my mind first is a conventional lithography, actually, like some top-down lithography, including the UV-based photolithography and the electron beam lithography, which have extensive employed. However, this lithographic technique involving electrons or ions, which will damage the 2D materials, and the resist residues may contaminate the dedicated materials, like the image from the Dr. Zhen's paper. The image shows here more like rounded particles are present in the 2D materials fabricated by e-beam lithography, and the flake damage happens at the edge. So besides the conventional method, actually many unconventional methods are developed, such as the laser aberration, also called laser cutting, laser reduction, and laser producing, processing. The laser method, the obvious advantage is remotely controlled non-advanced and it's one-step method with we don't need any mask, and the cost is low. Here shows the example of how to do the laser aberration. Actually, they use a laser director to destroy or to cut the graphene here, and then transfer the cutted material to any other substrate by the dry transfer method. But we all know like this method is limited by the optical diffraction resolution. So it's not easy to fabricate a sub-micrometer pattern, and the laser-induced the thermal effect or phonon effect will influence the device performance. So if we are going to pursue high resolution patterning, maybe scanning proper lithography is a good candidate because that is a direct writing method and rely on only a small, like a tiny tip, maybe tens or a few nanometer diameter. For example, here shows a result, the example of use a silicon tip to scratch the graphene oxide and create the nano ribbon, maybe the width about 50 nanometer. And this is it's a pure mechanical method. Another one is like chemical method is called oxidation scanning proper lithography. Combining the etching process, they can also cut or pattern the 2D materials at a high resolution. So besides the conventional and the laser, actually some bottom-up techniques are advantages for the scannability and the high resolution. For example, the material process, you can introduce the patterning during the growth, such like you can achieve the seeded growth of graphene again, and later on the graphene nano ribbon or graphene pattern use some during the material growth. But this method cannot fabricate a very complicated device structure. After you want to design other pattern, you cannot do it because it's designed during the material growth. So next, I will present you the patterning of 2D materials using thermal scanning proper lithography in your lab. First, let me introduce a little bit about the TSPL here. TSPL is short of thermal scanning proper lithography, which is developed by Heidelberg Instruments, previously called Swiss Litho, founded in the 2012. If you want to know more information, you can go to the website here. And our EPFL here have the one of the first tools in our lab. The tool actually mainly relies on the tiny tip, which can be heated up to over 1000 degrees C. Here shows the TEM image of the tiny tip. The diameter of the apex is about 5 to 10 nanometer. So it's a very, very tiny tip. Actually, besides the tip, recently we installed the laser components into the tool. It means we can also use the laser to pattern the structure, which speed up a lot dramatically for our patterning process. Actually, for this patterning, we have to combine of using some thermal sensitive resistor such as PPA. So in that case, we can transfer the pattern into the substrate such as silicon oxide or any other substrates. If you would like to know more information about the TSPL, I recommend you to have a look this review paper from last year published in the Microsystems and Nano Engineering. So use TSPL, how we can cut the 2D materials. Here I will show you the thermo-mechanical indentation technique for direct cutting of 2D materials at the nanoscale. In this technique, the heated nanotip is applied to the underneath of polymer to sublimate so that the 2D on top can be cut. The process is illustrated here. You can see first a 2D layer is transferred on top of the PPA with the van der Waals interaction. So there is no sliding between the 2D and the PPA. Then the hot tip approach to the 2D materials, and of course applied with sufficient high force, so such that the chemical bonds in the 2D layer can be broken. Meanwhile, the PPA underneath will sublimate and escape from the layer which result to the sublimation of polymer. In the end, a deeper indent can be created, and the 2D materials is removed here. So this is ideal. So how we do it? Actually, we first design a pattern consisting of some nano square arrays in monolayer molybdenum ditelluride. The set length we choose is about 50 nanometer and 70 nanometer here. The writing speed is about 0.5 millimeter per second, and it takes 45 seconds for the whole pattern of 2.5 by 2.5 micrometer square. And the depth is about like 20 nanometers. So which indicates like the indentation process creates the cut. Here's cut, it's not strain. Further, we demonstrate like the continuous cutting in a lab-listen pattern. From the topography, we can see like very sharp cuts are created in the 2D layer. Actually, the smallest feature we demonstrate here we can get is about 20 nanometer, which almost the smallest reported for the direct writing or direct cutting method, and is similar to the resolution of e-beam lithography. So not just applied in the monolayer ditelluride, also can be applied to many other 2D materials and also many different cutting patterns, such as molybdenum disulfide, MS2, MSE2, and also some heterostructure. But currently, this method is not achievable in the graphene. From the graph of the indentation, we can see here the indentation is about 3 nanometer. So we can see the significant strain is increased in the graphene, but not cut. So why we cannot cut the material, and what's the reason? Actually, there are two main parameters influence technical. One is temperature, another one is force or voltage. The temperature of the heater can be applied up to 1400 degrees C. This is the temperature of a heater, not the tip. Actually, the tip temperature is around much lower than the heater temperature. Is about like 40 to 70% of the heater temperature. So, for example, if we apply the 900 degrees C to the heater, the temperature of the tip is around 300 degrees C, even less. So, besides the temperature used to sublimate the polymer. Another parameter is force or voltage. So you can see when we apply the voltage to the piezoelectric cantilever, it will bend, and is also the spring constant. The spring constant will prevent the cantilever to bend. So at the end, we can get the indentation force by these two value. Based on our calculations, the force we can achieve, the highest force we can achieve is about 300 nanonewton, and the pressure, the highest pressure we can achieve is about 4 gigapascal. Experimentally, we also did some measurement or test to see to compare the parameters. First, have a look at the left two images here. We applied at like a low temperature, 500 degrees C, and either at like a low voltage or high voltage, we cannot cut 2D materials. It means the PPA is not evaporate, and the sublimation of PPA is essential for this cut. If you cannot make the PPA evaporate, you cannot cut the 2D materials. You only slightly strand 2D materials. So if then I will apply high temperature to make the PPA sublimate. So I apply at the 900 degrees temperature. So you can see at the high voltage or high force, we can easily cut the 2D materials, but at the low temperature, at the low voltage, we cannot cut. It means like efficient force is needed to break the 2D and to make the PPA evaporate and to have indent here created. From the calculation, we can see like the PPA plays a very important role in this technical. So what's happened during the process? Actually, during the process, the PPA will decompose into smaller volatile molecules. So in combination with the sublimation and the thermoplastical deformation, we can cut and strain the 2D materials, and both are durable. In comparison, we also tried the other polymers such as PMMA. We use the PMMA to as a substrate instead of PPA. Only thermoplastical deformation happens, so we can only strain the 2D. We cannot cut it. Here shows some result of straining of the MS2 on the PMMA. So you can see the indentation depth is about a few nanometer. So I think you may ask if the 2D materials is efficiently cut. Maybe you just didn't cut it, you just bend it. So we did some single alignment spectrum on the samples of like a Princeton area and some edge area and the cut area based on the alignment intensity. So you can see the intensity of the cut area is almost zero. It means there's no material in this area, and it means the cut area is successfully removed. This is for the single spectral measurement. We also have further verification method to provided by the Lyman mapping. Here you can see I patterned the microstructure of the on the one layer MT2, and the Lyman pattern corresponds to the AFM topography. You can see here is the intensity is much lower than the red area. It means this area, the 2D material is removed successfully. So we have developed this technique. Then we are going to demonstrate the concept of cutting the 2D devices. So the idea is simple, just to reshape the 2D layer. The 2D layers as the channel, we're going to like decrease the channel width or cut into like a nano ribbon arrays. First, we prepare the 2D transistors, then we're going to cut whatever we want. So the process is presented here. First, we spin coat a layer of PPA on the pre-patterned electrode, and then we use a laser writer to remove the PPA on top of the electrode. Actually, I mentioned before, the laser writer actually is the one component in the nanofraser tool. So then we, without the PPA on the electrode, we're going to transfer the 2D layer on top of the PPA and with two ends in contact with source and drain electrode. So here shows the device image. So you can see this color represents the PPA, and here's the gold is yellow, the yellow gold, and then here's the monolayer MT2 flake. And at the end, we're going to use hot tip. So here shows the result of the successively cutting the set bands a way to decrease the width of the conductive path. So image shows the topography of 2D layers on the substrate before cutting, after first, second, third, and the final separation cut. So you can see the width. We measured the width here. The first one is 4.5 micrometer, and then it's 4, then 3, 2, and at the end we separated the two the flake into two parts. Then we did the IV measurement to see the transistor performance. We can see the ID. The ID decreases with the cutting number. When we cut more, means the current will decreases. And we measure the sheet resistance. We can see its independence of the width of the nanomechanical ribbon. And the whole process actually we did in the natural atmosphere to avoid the oxidation. So I showed only one example of the device demonstration. Another one, but I think if you are interested, you can go to our paper to have a look at it. So in summary, we developed like a high resolution thermomechanical nanocutting technique. This technique is based on the TSPL, thermal scanning pulpal lithography. which avoid the electrons maybe that may damage the 2D materials. And the resolution we achieved here is down to like 20 nanometers. And for this technique, actually PPA or any other thermosensitive polymer plays a very key role in this technique. And this technique can be applied to many other 2D materials and even heterostructure. But we also meet some limits in the tip, such as the size of tip. If we can get a smaller tip, maybe we can increase the resolution. Another thing is the Young's module for the tip. We cannot apply like a higher force to the tip unless the tip will break. So we expect to have like the tip with higher Young's modulus, so which can provide a high force. So in the future, we will try new tips and maybe we'll implement the technique in the device fabrication. So next technique I will present is thermo-mechanical straining of the 2D materials at nanoscale. As we know, in the Intel of 90 nanometer technology, I remember it's 2013, and the strain silicon actually is applied in the semiconductor industry. You can see the compressive strain is introduced in the PMOS, and the tensile strain is introduced in the NMOS. And it turns out like the current, the drag current will increase by like 25%. So I think as well as in the 2D material industry or career, the strain is believed to bring like new things or boost the device performance for us. Like here shows the example how to open the band gap of a strain by strain. So like the strain at this value can open the band gap. So that's the band gap graphene. So that's graphene can change from the same metal to semiconductor. It may be used as a very good like in transistors. Besides the band gap of the graphene, actually it is widely used in the MT2 for the detector, because for the MT2 very good material for the used as for the detector. So the strain can boost a lot in the responsibility for the detectors. So okay, we know the application in the strain. So what's the state-of-art research or method in the strain engineering? Actually, there are basically 5 types of method. The first one is like you may know stretching or compressing or bending the supporting substrate, so you can, as well as you can like introduce the strain into the 2D materials. Another one is like you transfer the 2D material on top of the topographically patterned substrate, so you can locally strain the 2D materials. Another one is like you introduce the strain during the growth. So you can have the strain in the materials completely. This method can create strain before or during the growth or deposition of 2D materials, but they can only introduce global strain covering the large area. You cannot locally modify it. Which can locally modify the strain is scanning probes. It means, for example, if you have like a suspended 2D materials, you can use the tip to locally bend it, and the temporary strain is introduced into the 2D materials. Another, if you want to achieve the permanent strain, you can have the graphene or 2D materials on the solid state silicon oxide, such as silicon oxide substrate, and you create strain. But this method can only create really limited strain, because the solid substrate and the here they can only create like a 0.1% with about a 2 nanometer indentation depth. So if we aim to get the high strain and the local strain with the high resolution, here we developed the thermo-mechanical nanostraining technique to efficiently create the strain in the 2D materials. So the same as the nanocutting, we prepared the same materials. So we transferred 2D on the PPA with the van der Waals interaction, and then the hot tip applied with heat and indentation force approaches, and make the 2D deform, not cut, just deform out of the plane. so that the 2D layer will elongate, and so we can have the strain introduced in the 2D materials. Because after tip removed, the PPL will faster cool down and resolidate, so the permanent strain will be created. We believe this this nanostraining of 2D materials will contribute a lot to the modification of band gap, and in the future will improve improve the device performance, especially in the mobility and the off ratio and the speed. So we write many different patterns on the different materials. First, one layer MS2, we have the like a vertical horizontal lines with 4 nanometer depths and 6 nanometer width here, and more patterns in the maybe bare layer MT2, graphene, and MS2. So then we have to measure the strain in the 2D materials. We first employed the macro Raman, the conventional Raman spectroscopy to characterize the strain in the monolayer MS2. So you can see from the single spectral measurement, it shows like significant redshift of the two peaks. The blue one, the blue curve presented the unshaded one, and the red one is the strand sample. So it's red shift from the left. And for the Raman mapping result, confirm the red shift in the pattern area. So you can see the blue area corresponds with the pattern area. Then the band gap modulation is examined actually by the scanning photoluminescence PL spectroscopy, and then we calculate about the band gap modulation here, and based on the strain calculation, we can get the modulation rate. Oh. Okay, sorry, map going further for 1 second. Okay, now it's good. But you can see the strain is created at the nanoscale. We apply the macro Raman spectrum to measure it. Actually, it's not accurate. So we used a high resolution Raman to measure the strain. It's called a tip enhanced Raman spectrum. It's the FM based Raman spectrum. The resolution can go to like a tens of nanometer here. And this work is in collaboration with Professor Zenobi at ETH Zurich. So here we show the resolution of the measurements about 10 nanometer. Each pixel present like a 10 nanometer here, and then we can see the TERS map corresponds to the height map, and the strain we get from this nanostraining is about like a percent of like 2.6% maximum in the strain of the valley. So in about this high resolution thermomechanical nanostraining, I think we have achieved also like very high resolution, about 20 nanometer. This is almost the highest reported in the literature. And we use the PPA as a substrate. And the band gap here we can modulate is about 0.3 EV for the monolayer MS2 sample. And of course, we can also apply to different materials and to see to modulate the band gap of the 2D semiconductors. And in the future, we also would like to use new tips from Felix and maybe multiple tips to speed up the patterning process. And we are going to implement the strain into the device fabrication. So at the end, I would like to thank my supervisor, Jürgen Brugger, Professor Jürgen Brugger and my colleagues, Samuel, Anna, and Giovanni. I think it's Giovanni is here. Yeah, Giovanni, and also our funding from ERC and the Horizontal 2020, and the technical supports from our EPFL clean room, CMI. And thank you, audience. Thank you for your listening, and thank you. I'm ready for your comments and questions.